Okay. All right. In this video, we're going to talk about residence time distribution in ideal PFRs and CSTRs. Okay, so we discussed in a prior lecture that there is only one value for residence time in an ideal PFR or PBR, and that is because there is perfect mixing in the radial dimension and no mixing in the axial dimension. So basically all the fluid takes the same amount of time to travel from the inlet to the outlet. And maybe you recall I tried to do this animation, which maybe I'll try and do again a little bit more successfully. Maybe I shouldn't have done that. Basically, I have this tubular reactor, and let's see if I can just take that piece. No, I cannot. Actually, I think I know how to do this, so thank you for your patience while I work on this. So I'm just going to draw this plug. Maybe this is not making sense because really the plug wouldn't exist outside of the reactor. But basically, if I now put this here, once the fluid enters the reactor, it basically enters into some volume slice. I've drawn a finite volume slice here, but in reality it would be an infinitesimally small volume slice. And whenever it enters, it basically stays in that volume slice. Of course, it's going to react as it goes down the length of the reactor, but it's not going to diffuse, for example, into the next volume slice. It's not going, there's going to be no, this is an ideal PFR, so it's going to not have any residence time different than what it would have in this volume slice and what every other molecule in the reactor has. And it's plug flow, so every molecule within that volume slice is going to have the same exact residence time. What we mean by that is as this volume slice flows down the reactor, every volume slice is going to do exactly that, and and then henceforth every molecule is going to have the exact same residence time. So if I go back and try to repeat that same drawing, I have everything things enter here, they all flow through the reactor and exit, and everything takes the exact same amount of time. That's what's going on in an ideal PFR PBR. That was a poorly drawn arrow. I should, oops, do it like this. Okay. Okay. And so we said also that for a tubular reactor, the residence time distribution, E of T versus T, looks like this. I have a Dirac delta function. So here we have T equals the residence time of the PFR. And every molecule has that residence time. There is no distribution. We also said we could look at the cumulative distribution function. The cumulative distribution function tells us the fraction of molecules that have been in the reactor. It's really poorly written. For time then less than t, for a tubular reactor, this is going to be a step function. So once you get to that point on the time axis, all the molecules have the same residence time. So in this region, none of them have been in the reactor for less than that. And in this region, all of them have been in the reactor for less than that. That's basically all there is. So the tubular reactor is in essence simple, or at least the ideal tubular reactor is. We also discussed that CSTRs, even ideal CSTRs, are different, and that's because we have this really large volume. We enter stuff into the volume and it is immediately well mixed. So we basically have two conditions in a CSTR. We have that of the feed, and then we have that of the volume, and then what's exiting the CSTR is equal to that in the volume. So, and these things can be quite different. So imagine if you have a CSTR and you're operating it to some high conversion, the concentrations inside the CSTR are going to be quite different than in the feed. And that's going to be due to the fact that the CSTR is well mixed. So everything drops in and immediately assumes this new concentration. We said that to make that happen, what has to happen is that some of those molecules are going to leave almost instantly, and some are going to circulate and stay in the reactor essentially forever. Not like a very small fraction is going to stay there forever, but some amount will. And that's because of that we have a residence time distribution. So even in ideal CSTRs, there's a residence time distribution since some molecules will exit the reactor quickly, while others will remain in the reactor for a long time. So let's think about what this means. So how do we get the residence time distribution function for an ideal CSTR? To do that, let's consider a pulse experiment. So in our pulse experiment, what we're going to do, I'm going to draw that over here. We have our CSTR. What I'm going to do is I'm going to, actually, let me do this. I have a detector here. I'm going to measure C of T of my tracer. I'm going to initially inject T equals minus something very small, 0.0001 or something like this, just making a very small number. So what I want to do is inject the tracer. I don't want to I need to know how much tracer I injected, but I want to consider only the tracer coming out of my reactor when I do that, and that's because this is a pulse experiment. I'm basically going to put that tracer into the reactor, and then I'm going to measure it coming out, and that's going to tell me something about my residence time distribution. And I guess I should say, because I'm not going to account for the amount put in my mole balance, because I'm not going to continuously flow it in. This is not a step experiment. This is a pulse experiment. I should say inject known amount of tracer. So I'm going to inject that known amount of tracer, and then I'm going to start my stopwatch. Okay, so let's write a mole balance on that. I'm going to have an accumulation. I need that accumulation term. That's going to be what tells me what's coming out of the reactor. So I have dNA dt equals 0. And again, that's because I inject the tracer, and then I'm going to do the mole balance on the CSTR. I want to see what's coming out. So in is going to be 0. Out is going to be the volumetric flow rate times the concentration of the tracer. There's no generation or consumption because by design I've chosen a tracer that is non-reactive. Okay, so what I'm going to do here, I'm going to run this experiment under liquid conditions. So that means I've got constant volumetric flow rate. Also, I'm going to say that the volume of my system is constant, which is for a CSTR, I can absolutely do that. For CSTR, PFR, I can absolutely make that assumption, regardless of the phase of the material. So now that I've done that, I need to solve essentially this differential equation. First thing I'm going to do is get consistent variables. So I'm going to say that my Na, which is the number of moles of tracer, is equal to the volume times the concentration of A. That's going to be equal to negative volumetric flow rate times the concentration. Another thing I can do here is bring the volume as constant, so I can bring it outside of the derivative. That gives me this expression. I'm going to, since I'm interested in residence times, I'm going to divide through by volumetric flow rate. That is going to give me dCA dt is equal to, actually it would be, what? One second. It would be tau, correct? Residence time times dCA dt is equal to negative CA. What that then allows me to do, I can separate variables. So I'd have dCA over CA is equal to negative 1 over tau dt. And I can then solve that. That is going to give me, if I integrate that, 0 to CA dCA over CA equals negative 1. There's negative, hold on. Negative 1 over tau. Tau is a constant. It's just equal to the volume divided by the volumetric flow rate, which I've said both of those are constant. I would say 0 to T of dt. And what this should give me is CA of T is equal to CA not, I screwed up here, this should not be 0, it should be the amount of the concentration of the tracer that I injected, which is I'm going to call CA naught, times the exponential of negative T divided by tau. Okay, so that's going to be basically the concentration that I measure. So here at my detector. If I'm measuring my detector, I can get this function of concentration versus time. This essentially gives me my residence time distribution. Okay, so, or this is gonna, I'm sorry, this is gonna give me my CFT curve, my concentration versus time. To get my residence time distribution, I need to take that CFT curve and divide by the integral from basically the integral from time equals 0 to time equals infinity of CFT. So that's going to give me CA naught exponential negative T over tau divided by CA naught integral 0 to infinity exponential negative T over tau dt. So if I want to perform this integral, integral 0 to infinity exponential negative T over tau dt is going to be equal to, or approximately equal to, the limit as T goes to infinity, 0 to T of exponential negative T over tau dt, which is going to equal negative tau times the limit as t goes to infinity of the exponential of negative t over tau minus the exponential of negative t over tau, and this is going to be evaluated at t equals 0. So basically what I've done here is this piece here is the upper limit of integration, and I'm subtracting from that the lower limit of integration, which is this piece. So I'm taking that evaluated at 0. So I can't evaluate it at infinity, I can only take the limit. That's what I've done here. Here I have evaluated at 0, saying that in both, or in the integral of the exponential of minus t over tau is minus tau times the exponential of minus t over tau. Okay, so this piece here, actually I should say the whole piece, this piece equals 0 because basically I'm taking the exponential of negative infinity, the exponential of negative infinity is 0. This piece is equal to 1. So what I get my entire integral being is tau, the residence time. So that means that, and maybe I can give myself a little bit more room here. Okay, so what that tells us is that for an ideal CSTR, E of t is going to be equal to the exponential of t over tau divided by tau. That's my residence time distribution for an ideal CSTR. We saw in the last lecture that what that would look like is an exponential decay function. And this is where it gets that shape. And the axis is going to be time to the negative 1 units. And then this would be time units. And of course, if we integrate this function, so if we integrate e of t dt between 0 and infinity, we're going to get 1. So 100% of material eventually has to come out. Okay, so that is our residence time distribution function for an ideal CSTR. This is what the residence time distribution function for an ideal CSTR looks like graphically. We can also talk about a dimensionless residence time distribution function. To do that, we introduce a variable theta. Theta is equal to t divided by tau. The nice thing about this, when we do this, is that the dimensionless residence time distribution function is the same regardless of the operating conditions of the CSTR. So for example, regardless of the volumetric flow rate, etc., all dimensionless E of t, or all dimensionless E of theta curves for any CSTR are going to be identical. They're all going to fall on the same line. The dimensionless curve is the exponential of negative theta. So basically what this is tau times E of t. So basically we're multiplying here by the residence time, and once we do that, we get rid of differences that could be caused by different volume of reactor, different volumetric flow rate, etc. Similarly, if we wanted to look at the cumulative distribution function, the dimensionless one, that's going to be the integral from 0 to theta of E of theta d theta. So instead of integrating with respect to t, now we're integrating with respect to this dimensionless variable. That's going to be equal to this integral, which we can solve as being equal to 1 minus the exponential of minus theta. The other thing that we want to do, and we know what the answer is going to be, so we want to determine the mean residence time for our ideal CSTR, and spoiler alert, it's equal to tau. But we can prove that by writing the formula for mean residence time. That is going to be equal to the integral between 0 and infinity of t times e of t dt, which is going to be equal to the integral between 0 and infinity of t divided by tau exponential of negative t divided by tau. As you can see here, we could probably do this in terms of theta, but let's keep it in terms of t. Tau here is just volume divided by volumetric flow rate. It's a constant, so I can bring it outside the integral. Okay, so now I've got this integral to solve. It's a little bit more complicated than before. I'm going to solve it by integration by parts, which is a thing that I was really good at about 25 years ago, maybe a little more, maybe 26 years ago, that I actually had to look up and remember how to do. But basically, what we're going to say is the integral of u dv equals u times v minus the integral of v du. We're going to select here u is equal to t, du is equal to dt. I guess hence du is equal to dv, dt, dv is going to be equal to the exponential of negative t over tau dt, and v is going to be then equal to negative tau exponential of negative t over tau. So what that tells us is that the integral of t exponential minus t over tau dt is going to be equal to t times tau exponential of negative t over tau plus tau integral of the exponential negative t over tau dt. This is going to be equal to negative t times tau exponential of negative t over tau minus tau squared exponential of negative t over tau. That's our indefinite integral, but we need 1 over tau integral between 0 and infinity of tau exponential negative t over tau dt, which means we need to do limits. So let's say it's going to equal the limit as t goes to infinity of t exponential, here I've divided through, I should note here I've divided through by tau because I had to recapture my original formula. So my original integral, I divide everything through by tau. So what I've done here is take out this tau and one of these taus. So I'm taking my limit then of t times the exponential of negative t over tau as t goes to infinity minus tau times the limit as as t goes to infinity exponential negative t over tau, and then I'm going to subtract from that. So this is my evaluating at infinity piece. I'm going to subtract from that the evaluating at 0 piece, which is going to give me 0, t equals 0, times the exponential of 0 minus tau times the exponential of 0. So in doing that, I'm evaluating at t equals 0. Okay, so let's go through and look at these different expressions. T is going to infinity. This term makes that 0. T is going to infinity. This term makes that 0. T is equal to 0. This term makes that 0. Here, tau is just tau at some value. This piece equals 1. So the entire integral, 1 over tau integral 0 to infinity t exponential negative t over tau dt is equal to tau. So for an ideal CSTR, the mean residence time equals t CSTR. So no big surprises there.